Hey, welcome everybody to the next lecture of Functional Programming 101x. Today we're going to talk about list comprehensions. And list comprehensions are a mechanism to write code that manipulates collections. And if we look at most programming languages, most of the features in a programming language has to do with dealing with collections. If you look at a traditional imperative language, such as Java or C#, it has a wide range of mechanisms to deal with collection. For loop, while loops, do while loops, for each loops, continue, break, and all these constructs are there to iterate over collections. Now, of course, mathematicians have been dealing with collections for centuries, and for mathematicians, the favorite collection type is sets. Sets, however, are computationally a little bit awkward, because when you have a set, it means that duplicated elements are removed, which implies that you need equality to deal with sets. And especially in a functional language like Haskell, it's very hard, well, impossible, you have to solve the halting problem to decide equality between functions. So what Haskell did, it took some of the ideas that mathematicians have used for a long time to deal with sets and simplified them to work over lists. And lists are my favorite collection type. And the reason is that a list just gives you the bare minimum to deal with a collection. You can, as you have seen, if we have a list that's composed out of a head and a tail, you can decompose that list recursively by just picking off the first element one by one. And that's very convenient. And so it puts very few restrictions on the collection type, unless sets where you assume equality of the elements, or arrays where you assume constant time indexing. So sets are, in some sense, the most pure form of collection types. And in Java, Java 8, they call these lists streams to emphasize that these are collections where you can only access the elements one by one. And in that sense, Haskell lists are an example of Java 8 streams in that philosophy. All right, let's look at how mathematicians use so-called set comprehensions to define sets. Here's an example of a set that it's a set of all squares with values between 1 and 5. So it's x squared, where x is taken from the set of 1 to 5. So the result of this is the set 1, 4, 9, 16, 25. But as I said, if we take x to range over functions, then this becomes really hard to implement. So what people did in functional languages is take the same notation, the same ideas, but instead of sets, use lists. And so set comprehensions for mathematics become list comprehensions in Haskell. And here's the same example written as a list comprehension. So here you see it's the list of square numbers x squared, where x is taken from the list 1 to 5. So here you see this, you read this as x is taken from the list 1 to 5. And if you evaluate this, you will see that this returns the list 1, 4, 9, 16, 25, but is a list, not a set. The expression x taken from 1 to 5, that's called a generator. And the reason it's called a generator, because it defines how to generate values for x. All right, so x is taken from that set. Of course, since everything in Haskell and that's a good aspect of programming language, has to be compositional, so you should be able to just recursively use the same structures over and over again. comprehensions can have multiple generators. And here you see an example of that. So we take all pairs x, y, where x is drawn from 1 to 3, and y is drawn from 4, 5. And what you see is that the y varies faster than the x. So the result list is 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. And so another way to look at these nested generators or multiple generators is like a nested loop, where the y is the inner loop and the x is the outer loop. So if we swap the order of the generator, then now x varies most quickly because this becomes the inner loop. So what we get now is, but notice that we still have here x, y, so we only swap the order of the generators, not the order of the variables. So now instead of this guy moving fastest, we get the x moving fastest. So the result is 1, 4, 2, 4, 3, 4, etc. And this notion of generators, you will recognize that in many, many programming languages. So in Haskell, these are list comprehensions. If you use Python, it also has list comprehensions. Scala has 4 comprehensions. F# has comprehensions. C# and Visual Basic have link comprehensions. And if you look at a language like SQL, which is completely built on top of comprehensions. Only there you don't write them this concisely, you write select from where, etc. But it's basically the same idea. So by studying list comprehensions in Haskell, you will be well equipped to use the same ideas in whatever language you encounter them in. All right. Now, we have seen a few simple examples with generators where the generators only had constants. But generators can also depend on each other. Just like when you have a loop, the inner loop can use variables from the outer loop. And with comprehensions, that's no different. So if we look here, we say x is drawn from 1 to 3, and then y is drawn from x to 3. So x is in scope in the generators that come after it. And if we execute this comprehension, we get the list 1, 1, because y is drawn from 1 to 3, because x starts out at 1. So we get 1, 1, 1, 2, 1, 3. Then y is exhausted, so we're going to check the next value of x, so that will be 2. So now y is taken from 2 to 3, so we say 2 to 3. And then the last iteration, we take x to be 3, and then y is drawn from the list 3 to 3, so that is the last value is just 3, 3. But again, you're totally familiar with this because this is the same how nested loops work in any language. So the inner loop can use variables defined in outer loops. One of the nice things of comprehensions, and especially of dependent generators, is that you can write very concise code. For example, if we want to take a list of lists and flatten them into a single list, we can do that with the following comprehension. So we say, just give me every list out of that list of lists, and then just give me every element of that list and return that. So this is a doubly nested loop that goes over every list in this list of lists and just yields all the values to return a single list of type A, of the same element type as the original list. So when we concatenate 1, 2, 3, 4, 5, and 6, the result will be 1, 2, 3, 4, 5, 6. All right? So very, very concise code that we can write using comprehensions. Now the next thing, beside generators, that you want to use in a comprehension, and that's also used a lot in set comprehensions, is to allow filters. You want to, have X drawn from some collection, but you want to throw out certain values for which a predicate does not hold. So for example, if we want to have all the even numbers between 1 and 10, we can just say X is drawn from 1 to 10 and filter out only the even numbers. So the result of this is the list 2, 4, 6, 8, 10, the even numbers between 1 and 10. And in SQL, you will recognize this as a select where. So the where clause here is called a guard in Haskell. And if you use LINQ, list comprehensions, or comprehension syntax, that will also be called where. Here's a example that uses guards to take a number and break it down into its factors. So what are the factors? Well, we take a number n, we take all the numbers between 1 and n, and then we check, we only retain those for which n modulo x is 0. So the factors are 15, so we start out with all the numbers between 1 and 15, and then we throw out all the numbers for which n modulo x is not 0, and in this case, the factors are 1, 3, 5, and 15. And then we can use this factors function to define a very simple predicate to check whether a number is prime. So number is prime if the factors of that number are exactly the list 1 and n. For example, 5 is not a prime because the factors are not just 1 and 15, it's 1, 3, 5, and 15. But 7 is a prime because you can check by using GHCI or your own favorite programming language that the factors of 7 are 1 and 7, and so we decide that 7 is a prime. Okay, so if we want to now check whether, what are the primes up to a certain number, well, we can write this simple list comprehension. So we say, give me all the numbers between 2 and n, where n is the parameter to this function. And then I only want to kind of maintain the prime number. So I filter out all the numbers that are not prime. So if I want to have all the prime numbers up to 40, I just run this list comprehension and I get all the prime numbers. Now, of course, this is not the most efficient way to compute prime numbers, but I think it's a very nice illustration of using list comprehensions. So see you in the next chapter.